Hi, everybody. Welcome back to the Machine Learning for Health seminar at the Broad. And today I am delighted to welcome Dr. Akshay Chaudhari from Stanford. He is an assistant professor of radiology and biomedical data science, but then also wears several other hats. He is the interim division chief of the Integrative Biomedical Imaging Informatics section in radiology, the co-director of clinical AI at Stanford Radiology, and also the Associate Director of Research and Education at the Stanford AIMI Center. He leads the Machine Intelligence in Medical Imaging Research Group, focusing on improving acquisition and analysis of medical images and related healthcare data. And so his talk today is entitled Generative Models for Text and Images Development and Evaluation. Thanks.
Thank you so much, Danielle, and thank you so much for the kind invite to speak at this seminar. For the next, 40 minutes or so, I'm excited to talk about some of the new tools that my group is developing, both for the analysis of clinical text as well as the analysis of medical imaging. I was told this is a group with a lot of broad interest, so I tried to have a little bit of both features included in there. And really, the focus of this talk will also be not just how we can develop some of these next generation models, but how can we critically evaluate them for tasks that will actually be beneficial in clinical settings? And specifically, how do we focus on scalable evaluation of some of these tools? So hopefully that'll be the little bit of a flavor for most of this talk. I'd like to keep it as informal as possible. I'll try to keep pausing after a few slides or so, just to see if there's any question or feedback from the audience. So feel free to let me know if you have any questions. So just getting started, here are some of my disclosures. None that will affect the content of this presentation. I'll just be sharing some of the open source academic work that we've published previously. So I first wanted to talk about this broader notion of foundation models. I'm sure this is a term that almost all of you have heard before. And this is really a different way about thinking about a lot of the AI models that are being developed. Rather than developing these task-specific models that usually do one single thing, this notion of foundation models really involves aggregating a large amount of data, and usually this data is unlabeled. So there's no human-generated labels for specific tasks that we want to be able to perform on this data. And whenever we aggregate large amounts of these data sets, and these data sets could be across modalities, it could be text, it could be imaging data, video data. In healthcare, it could be EHR data sets, omics, wearables, etc. Effectively, if we can aggregate data at scale, there are useful representations that we can actually extract from these data sets. And that's exactly what a foundation model tries to do. Once we have large-scale aggregated data, we can train self-supervised learning algorithms that do not require human-generated labels, but we're learning from the innate nature of the data itself. And once we've trained this foundation model in a self-supervised manner, the benefits that this model provides is that the same monolithic model could actually be applied to a variety of different downstream tasks. And maybe this application could be in a zero-shot manner, which means that you don't need any examples of that particular task, or it could be in a few-shot manner, where you can adapt the model using one or two examples of the task that you're trying to perform. And generally, we've really seen most of these foundation models take the flavor of being text first. So, if we look at the OpenAI models, the models from Anthropic, et cetera, most of this really rely on having a really high quality foundation driven by text and natural language understanding. And once we have this understanding of text, we can basically add more modalities to this language model to really convert it from a unimodal language model to a multimodal language model. And a lot of the applications that my group is interested in is really how do we take some of these models and apply them to clinical tasks that we cared about? So I wanted to first start by describing a study that we conducted almost a year and a half ago now that really tried to focus on this task of clinical text summarization. And we wanted to be able to use language models to be able to perform this task. And the reason we chose summarization as a task was because we did not necessarily want to rely on the innate knowledge that a model may have about medicine. We wanted to really constrain the scope of activities and the extrapolations that a model has to perform. So basically, at a high level, summarization of the task takes in a large corpora of text as an input. And we're basically trying to convert this large amounts of text as an input into some bite-sized conclusions that a human can readily ingest and to be able to make decisions on. So hopefully, going from this large input to a smaller input requires limited medical knowledge that a model actually has. And that was the reason that we actually chose this task in the first place. So I just wanted to walk you through the study schematic that we had for this particular task. So we chose a whole host of different models, and I will say that we performed some of these experiments almost, 18 months ago. So these were some of the latest generation models that we used back then. We wanted to use a lot of open source models that we had available to us, and we wanted to use proprietary models that had high levels of performance. But given that we knew that there's likely a domain shift between general domain knowledge as well as clinical knowledge, we also wanted to come up with different adaptation mechanisms where we can convert these models to having more knowledge about medical text. And we had two different ways in which we tried to perform this adaptation. The first method was low rank adaptation. And this is basically taking any models where we have the open weights available to us and simply fine tuning the model for the instruction tuning data that we're creating. But obviously, this does not apply to some of those GPT models that could not be fine tuned. So, in that particular setting, we also chose an adaptation strategy called in context learning. And in context learning can be applied to pretty much any language model that we have. And the way it works is actually quite simple. If you want a model to perform a particular task, in the prompt itself, you can append some examples of that particular task. So you're basically taking question answer pairs to give the model an example of what sort of responses that you're looking for. And this allows the model to better understand the specifications of what you're asking it to do. And we showed, and this has been pretty broadly shown across all language models, that this in context learning is actually a really simple way to be able to improve your task performance. And then once we took these models and different methods, we wanted to apply them to a few different medical tasks. So we looked at different domains. I do a lot of imaging research, so radiology was near and dear to heart. We looked at progress notes, patient health questions, patient-doctor dialogues, and we chose this because this is where we're seeing a lot of excitement by hospitals to be able to implement some of these tools. Right now, ambient scribes are very common too, so we really wanted to assess this patient-doctor dialogue. We wanted to look at progress notes to understand whether or not models can actually come up with the right problem list. So we wanted this to be clinically relevant, and we wanted to choose open source data sets so that our work could be easily replicable. So this was a problem scope that we had. And then, since there's a lot of different models, methods, and tasks, we wanted to have some typical metrics that people use in the NLP domain to be able to crown some winners from these models. But knowing that these quantitative metrics don't necessarily reflect real world performance and real world expert opinions, we also wanted to choose the best model and the best method for adaptation and conduct a very rigorous clinical study with 10 expert physicians. So we had 5 hospitalists and we had 5 radiologists who looked at the best model and the method that we found. And in our evaluation, this best pairing was really using the GPT-4 model as a baseline and then using in-context learning. So effectively what we're able to do was if the GPT-4 model had a particular sequence length, we would pack the entire prompt with multiple examples of that QA task that we would have so that the underlying GPT-4 model had as many options or has had many learning examples from the prompt itself to perform the task of interest. And then we really wanted to understand how do some of the clinical readers incorporate this information. So in our reader study, we basically had a A/B test that we performed. So we provided the physicians the input, and then we provided them with 2 different outputs. And those 2 outputs were either the ground truth that were physician generated, or they were generated from GPT-4 within context learning. And using those 2 outputs, we simply asked our physicians which summary was the most complete, which one was the most correct, and which one was the most concise. And we really wanted to assess this on some sort of quantitative scale. Based on our scoring mechanism, if the score was close to 10, then that means that the humans always preferred the language model summary. If the score was -10, the humans always preferred the human summary. And going into this, our hypothesis was that, gee, wouldn't it be great if most of the responses are close to zero, which would mean that the model is actually non-inferior to the human summaries. But we're actually surprised when we saw some of these results that across the tasks for metrics such as completeness and correctness, we saw that the humans significantly preferred the model generated summary. And interestingly enough, our conciseness numbers were actually not inferior. What that really meant was we're actually able to be more complete and correct without it actually coming at the cost of conciseness. So we're not necessarily being wordy, we're not necessarily being verbose. We're packing in the same amount of information in a short amount of tokens. So we're very excited to see that our panel of expert physicians consistently saw that they preferred the language model summaries. And then we actually wanted to go one step beyond this too. We really wanted to see, what could be the potential harm if we simulated a scenario where we chose the incorrect summary. So in this particular case, what is the likelihood that mistakes made by medical experts might be better or worse than mistakes made by the LLM itself to be able to perform this harm analysis? And we saw that it turns out that medical experts and the mistakes that they make have a higher extent of potential harm that can manifest to the patient because of the errors in the summaries that they're generating. And similarly, both medical experts and our LLM had similar likelihood of that harm happening too. So this isn't necessarily a scenario that would be happening in the clinic directly, where we're just simply taking the language model summary. No one is checking it, but everyone is making decisions off of it. But that is the real scenario that we wanted to look at over here. And it was interesting that both physicians and models make mistakes, and that the extent of those mistakes are roughly similar between both of those two. So this just made us a little bit confident that there is potential for these language models to be used to be able to summarize clinical text. And all of these summaries were very helpful. We're able to conduct the study, but there are a lot of the challenges that we also faced with this, especially when we're trying to use language models for the analysis of clinical text. So we saw a lot of promising performance, but we could only do this after very rigorous evaluation. And this evaluation was really led by a lot of the physicians that we had, but this is not really scalable. If we're really trying to think about deploying some of these models at a hospital scale, we're not going to have physicians come up with evaluation criteria for all the different tasks, come up with a panel to assess inter-reader agreement, and so on. So one of the next questions that we had was, given that these tools are promising, how do we try to get them to the next level? And this is where we really wanted to rely on this notion of using language models as judges themselves. So instead of using humans to perform evaluations, what if we use other language models to actually evaluate the output of some baseline language model? And this was the motivation of some of our very recent work that we put out as a preprint a few months ago that we called MedVal. And the goal of this MedVal is we want to be able to build a large language model as an evaluation mechanism. So instead of having physicians review the outputs of language models, let's just do that with a language model itself. And the study followed a pretty similar schematic as the prior study that I showed. We once again choose some of the latest and greatest models that we had access to, using a mix of both open source as well as proprietary models. And then we had different adaptation methods here also. We could just use these judges in a zero-shot manner, just with simple prompting, or we came up with this fine-tuning process, which I won't really go into too much detail for this particular talk, but effectively we were able to fine-tune almost all the open source models and as well as the GPT models in a completely self-supervised manner. So we're able to generate synthetic data, and we're able to fine-tune all these models to be high-quality judges using a synthetic data pipeline. And we again wanted to evaluate this across multiple different tasks. And the goal of these tasks was to assess whether or not language model generated outputs were safe or unsafe, whether there's any risk in releasing this information to downstream physicians or clinicians. So to be able to assess that, we came up with this benchmark that we called MedVal Bench, where we had, once again, 12 physicians actually providing detailed labels about the safety of these LLM outputs. And then we compared that to these language model as a judge outputs too. And we simply wanted to see how close can a language model actually get to physician level ratings of evaluation. Because if we can get close, then these language models are essentially infinitely scalable across all responses, assuming that they have good enough quality. So the task here that we had was for every language model generated response, we wanted to perform a classification, whether the output has no risk, whether it's low, moderate, or high risk, because we're really using this in the context of whether or not this language model output should be used in any downstream care. So if there's no or low risk, then we can probably use the output pretty reliably. But if it's moderate or high risk, maybe we want a human to review it. Maybe we don't want to send out the answer. That was really the framing for this study. So here are some early results from this MedVal work. When we used open source models, such as the Llamas, Qwens of the world, we saw that our MedVal-based fine-tuning work can actually significantly enhance the evaluation capabilities that these models can actually have. It was actually pretty interesting to see that the smallest Qwen model actually outperforms the Llama models, even in a zero-shot manner, but that performing this MedVal-based fine-tuning further improves the accuracy of this safety check. And then we actually saw that these results stayed pretty consistent even when we used proprietary models such as GPT-4o, Mini, as well as the base model, because we have the ability to fine tune specific endpoints for these models too. So these were much better than the open source models, but we see close to a 10% improvement even with these proprietary models that have very high performance too. And this becomes quite relevant because depending on what sort of implementation system that you have, especially if you're trying to build agentic workflows, sometimes your token costs for these proprietary models can be quite expensive. So you might want to use some sort of smaller language model that you might be able to quantize, run locally. And these small models work pretty well as evaluation. And in particular settings, maybe you just want the best possible model independent of the inference costs or the latency, and you still have the capability to do that. So this was just our first pass at understanding what the capabilities of language models are, and then trying to build scalable systems that we can potentially use to deploy them in clinical settings. So maybe I'll pause to see if people have any questions about this first part of the talk, focusing on language model summarization as well as evaluation. I'll pause.
I had a quick question. So for
Please.
the summarizations, even that the people do, humans, that are high risk of death and so on, can you give an example of what that looks like in practice?
Yeah, so one of the most common modes of failures that we saw that humans make are actually laterality errors. So for example, let's say if someone is analyzing a radiology report from a chest X-ray scan, and there's a pneumothorax, which is a collapsed lung, it needs to be attended to immediately. Well, instead of saying that the pneumothorax is in the right lung, which was correctly identified in the findings part of a radiology report, the impressions might say the pneumothorax is in the left lung. So we found that that was a very common source of mistakes humans make.
Mm.
And then it was funny because we asked all our evaluators to also annotate anything that they found interesting in the impressions. And there are a few examples where our annotators were very sure that the response that they were evaluating was a language model generated response because random diagnoses for diseases were made up in progress notes, and there was no information anywhere in the patient's chart about that. Turns out that was a human generated summary
Wow.
too. So, I think the goal here isn't necessarily that language models have to be perfect, but I think just understand what is the baseline error rate that our physicians make is really useful to know too. And I think especially these days when our physicians are overworked, when they have to see a lot of patients, have to read a lot of studies, there's going to be errors. Hopefully, these errors are not severe or life-threatening, but just being able to calibrate for that in the first place could potentially be useful. So I thought that was pretty interesting.
That's interesting. Thanks.
Yeah.
Hi, Dr. Chaudhary. I had a quick question, perhaps a basic one. You mentioned in the reader study results slide that you performed a harm study.
Yeah.
I was just wondering how were you able to quantify harm in this case? Like, what is the general process for doing so in these kind of studies?
Yeah, that's a really good question. We had to learn that too. So we basically use the AHRQ, and I'm actually blanking on this, but there's actually a very systematic set of questions that can be asked. And the hypothetical situation that we're with when we conducted our reader study was we instructed our physicians to say there's a particular input. Maybe there's a finding section from a radiology report. And then there is some language model or human generated summary of this. That summary has a mistake. What would happen to the patient if that mistake were to be completely ignored throughout the care process that a patient might be getting?
Mm,
So maybe in a hypothetical setting, if you're trying to do an ACL surgery on the right knee, what if somehow your surgeon operates on your left knee? What is the extent of harm that would happen to the patient? What is the likelihood of that harm? And we were treating this in a situation where no one else is actually checking that particular note once again, which is not necessarily, very clinically appropriate, but we wanted to take the most extreme example that no one evaluates that summary. But hopefully that kind of describes what the framing of this particular study was.
absolutely. Yeah. Thank you so much for going through that.
Yeah, of course. Any other questions? Okay, I will continue moving on. So just okay. So now I really wanted to maybe shift gears a little bit, trying to look at multimodal responses too. Right now, the summarization task as well as the evaluation task that we've been looking at primarily only dealt with language as an input. But now there's a lot of really nice methods such as BLIP, which is known as bootstrapping language image pre-training, which relies on a lot of multimodal image understanding methods too. And one of these is known as CLIP. I was going to do a deep dive into this, but I think for the interest of time, I'll just describe how people and some of the frontier labs are effectively converting your unimodal language models into multimodal language models. So this is a pretty common setting where when we're trying to build a multimodal model where you can have a particular prompt, let's say write a romantic message that goes along with this photo. That is a instruction that you're giving the model, and then you have some multimodal input. In this case, it's a particular image. And then what you want to do is you want to use some baseline image encoder that you might have. This could be a vision only encoder, it could be a vision language pretrained encoder with CLIP, and you want to reuse some sort of large language model that your group or your company has trained already. And you ideally really want to keep this frozen so that you don't have to relearn any language capabilities. The way you do that is using this notion of collecting this triplet data set where you would have the image in your training data set, you have a particular query that you're asking of that image, and then you have an answer. So you're creating this really nice triplet, and then you're trying to reuse your image encoder. It could be your favorite encoder and your favorite language model. And what you're simply doing is you're training this little adapter, or this, initially the authors call this Q-former in the original Blid paper. Now people just call this term an adapter. And we are training this end to end, where the image would be an input into the image encoder. Your query would go into this adapter, and then the large language output, model output, would be the particular answer that you want this model to solve. So effectively, when you're going from a unimodal language model to a multimodal language model, you're effectively just taking your image, you're encoding it, and then you're training this adapter to convert image representations into representations that a language model might know to interpret anyway. And the hypothesis here is that our language models are very good. We know how to train them, they're very scalable. So, what if we make everything in the world look like language? That is how these models are being trained right now with these triplet data sets. So that was just a little bit of 101 on this blip style training and this method. Blip 2 is a very popular paper for these multimodal language models. Other approaches are pretty similar. They're known as LABA, but the underlying premise remains the same. So effectively, we have this triplet data set, and we wanted to see how can we use some of these LLM capabilities for medical imaging contexts. So what we're able to do with this particular approach was we're able to build a model that can interpret and understand chest x-rays. We're able to create roughly 6 million example triplets where we had an image, where we had some sort of querying text, and then we have some answers. And then we're able to train our own multimodal language model that we call checks agent in this particular case. And here's an example of what some of the training data for this could look like. We have an image, we have a particular question that we're asking of that image. Where is the opacity located? And then we have an answer that we want the model to be able to provide. And we train this using that blip approach that I described previously. And then we evaluate this across a variety of different tasks and across data sets. And I wanted to mainly focus on one set of tasks that we evaluated, which is taking a medical image and then generating the entire radiology report that a radiologist would be writing of that image in the first place. I think there's a huge shortage of radiologists in the world. Imaging volumes are increasing quite a bit. So if we can potentially use these tools as a co-pilot for radiologists, maybe there's value to be had in improving efficiency as well as improving accuracy that our radiologists have in light of the growing volumes. So that was our question that we wanted to address. So we really wanted to see how can a good model really be used in a clinical setting. So we conducted another reader study to simulate this. So we started off with arbitrary images that a radiologist would be reading anyway. And we wanted to mimic the academic medical framework of how images are interpreted. And in the academic setting, first, residents take a first stab at generating the report. So we asked residents to generate a draft report that they would be doing anyway. And then in a different group, we had residents working with this checks agent model too. So instead of starting from scratch, we had checks agent produce a report already that the residents could potentially modify. And then we tried to time how long does it take on average for the residents to come up with their reports, which took roughly 2.5 minutes in this case. And then we had a different group of residents that were working with this checks agent model that took substantially lower time to be able to generate their initial report. But this was just an initial report. We wanted to see whether a board certified musculoskeletal radiologist, sorry, it doesn't have to be MSK, was finalizing the report. And that's how this academic model works. Residents draft, attendings check it. And then we saw that it takes roughly the same amount of time for the attendings to edit and modify both sets of reports. And what this basically allowed us to glean was the reports that are drafted with the checks agent assistance don't necessarily have more mistakes or require more edits. It takes the attendings the same amount of time. So this workflow was really nice to show that a lot of these models can actually improve efficiency of the diagnostic process. But efficiency is just one side of the coin that we care about. We also want to ensure accuracy. So we asked all the residents and attendings that were participating in the study whether the drafted report by this particular model actually answers the clinical question for why the imaging was asked for in the first place. You know, plus 10 means that the report quality is fantastic. Minus 10 is it's just atrocious. So we first asked our residents who are using this model to rate the checks agent outputs, and they roughly agreed that the drafted report answers the exam indication. So that was a really good sign from an accuracy standpoint. Then we asked our attendings to rate the checks agent reports, and they also generally agreed, but they're more critical than the residents, which makes a lot of sense. Attendings have a lot more experience, they've seen a lot more diversity of cases, and they're probably more discerning in the model outputs. But they still generally agreed that the responses were good. And then interestingly, we also asked our attendings to rate our residents in terms of the quality of the reports. And this was roughly within the same ballpark too. So we thought that this was a really nice study that could show what is the workflow that a lot of these radiology drafting assistance tools could take in a hospital setting, and what is the value to be had. So I think the value is that there's definitely efficiency to be gained, and there could potentially be improved accuracy too, depending on what is the underlying capability that these models had. But this was a nice first pass that we were able to take to explore this workflow. And once again, evaluation is always a challenge. In this particular setting, we had residents evaluate, we had attendings evaluate, and similar to the MedVal work, we actually wanted to come up with an automated LLM as a judge evaluation for this too. And this is what led us to develop this green metric. So green is a score that we're able to come up with to assess the quality of radiology report outputs. And what we really like about this is that it gives a quantitative score, but it also gives a qualitative error summary in terms of where is your model making mistakes? Are these mistakes clinically significant? Are these models going to potentially have harm for the patients? And we can do this at a per report level, or we can do this at an aggregate level too. So we really want to use humans to verify at a first pass, but then we want to be able to have verification at a large scale scalable level too. And we're really excited that our green metric allows this evaluation to be quite scalable. And the other thing an automated metric like green allows is really creating some of these compound agentic systems where we're using our LLM as a judge, we're using our generator to actually improve the baseline generator in the first place. So let's see how we do that. So we presented this work a few months ago back at ACL, where we can start off with an arbitrary X-ray. We pass it through a frozen report generation model. So let's say we pass it through checks agent, but this could be any model that we're using. And then because most of these multimodal language models are inherently probabilistic, we can actually sample a variety of different output reports for the same given image. So either report one or report two, and we can generate as many reports as we would like. And ordinarily, we would need some sort of human judge to say, of the 10 reports, report number 7 was my favorite. This would be really hard because then the judge would have to read multiple reports. They'd have to do this across multiple different imaging studies. So it wouldn't necessarily be scalable. But then what if we replace this human judge with some sort of automated system like Green, which can automatically look at the original report and all these candidate reports, and then provide feedback that one of these reports is optimal. And now, once we have this understanding of which report is actually optimal, we can go back and we can update our generator model in the first place to create these reports that are preferred by language model. This is very similar to this notion of reinforcement learning with human feedback, where we rely on the stochasticity of models to generate a variety of different outputs. And then we use an evaluator, either human or AI, to reinforce a particular reward model. Like, what would a human prefer? Are there mistakes in this particular prompt? And that's really what we're seeing, especially as new reasoning models are coming up, that whenever we have verifiable rewards and a high quality reward model, we can actually use that reward model to improve our baseline language model in the first place. And this is what we tried to simulate in our study. And just in this entire closed loop framework, we're able to see roughly 10% improvement across almost all our metrics using this fully closed loop and using this fully automated approach. So this reinforcement learning with AI feedback really is easy to scale. It does not require a lot of human supervision, and just allows us to have lots of capabilities without needing expert human labels, which are always in demand. So maybe I'll pause again to see if this group may have any questions about some of the early report generation work. Okay, if no questions, then I will continue going through the talk. So far, as we look at some of these multimodal vision language models, they're primarily limited to 2D images. So most of the work in this domain has been limited to these chest X-rays, which are quite ubiquitous, but there's a lot of other more complex imaging modalities. And one of the Achilles heel of most of these methods is that they really only work well when you have short captions. So if you're training your clip models, or if you're generating these BLIP2 cell models that require long form outputs, there is a tendency for models to be degenerate when you're generating really long context lengths. So these are the two main challenges that we see. And we wanted to be able to take a first stab at trying to improve the capability of some of these radiology foundation models. So we're excited to create this model that we call Merlin. Merlin is a natively 3D foundation model that can allow for the interpretation of abdominal CT scans. And the reason we chose abdominal CT scans is because they're ubiquitous in healthcare. They are the most common volumetric imaging modality globally. And excuse me, um, and in the US, roughly 25 million unique patients get an abdominal CT scan per year. So they're very high resolution, high dimensional, and they're common. So if we have any model-based assistance, this could potentially help in a lot of clinical workflows. So towards this notion, we're able to pre-train Merlin with around 20,000 CT scans that we extracted from Stanford. And we're able to jointly train this model using all the corresponding radiology reports and all the ICD codes that were assigned to the patient at the time of their imaging visit. So we're really trying to reuse all the healthcare information that we have about these patients to train our Merlin model. And we really wanted to focus on eval. So we evaluated on roughly 5,000 data sets from Stanford and over 40,000 CT scans from 3 different hospitals in the US. And we also wanted to evaluate its out of distribution capabilities. We trained the model on abdominal CTs, but then how would the model work if we somehow just use it as an embedding model on chest CT scans? We wanted to see how well does it perform as an embedding model. So at a high level, when we wanted to train this model, one of the 2 training objectives for the model was to take your entire 3D CT scan, pass it through an encoder, and then simply try to predict the ICD code that was assigned to the patient at that particular visit. The reason we do this is because it's a pretty common task that, ICD codes will be assigned to patients, and we want to use this in lieu of different self-supervision strategies. Here, we're using the ICD codes as weak supervision because we want to learn general purpose representations with this particular image encoder. And then we also have this multi-modal clip style loss where we take the embeddings that come from an image encoder, we take the embeddings that come from a long form CT report, and we try to project them to be similar. This is the methodology that's known as contrastive learning, clip style learning. And we had to make a lot of modifications to how we actually make the model learn with these radiology reports, because unlike chest x-rays that have maybe 100 tokens, CT reports are really long form because they look for a lot of different findings, and they can have anywhere up to 500-600 tokens on average, with some scans having around 1,000 plus tokens. So we had to come up with different strategies to split our report into bite-sized components to allow for this model to converge. And after this model has been trained, there's a lot of tasks that we can perform without any adaptation itself. So just this pre-trained model. The first task is the zero-shot findings classification, which I'll talk about a little bit more on the next slide. Besides that, we can accurately predict different phenotypes that correspond to the ICD codes, and we can do cross-modal retrieval. And this could be really interesting in a lot of oncology contexts, especially where we may want to ask that for a given patient that I have today, is there anyone else in my clinical archive that this patient looks similar to? And if I have some known outcomes for that similar patient, maybe I can use that information to guide the therapy for my given patient. And we can do this with imaging, we can do this with text, and we can do it with both. So it just has really good retrieval capabilities. And once we adapt this model using more supervised data, there's a lot of different tasks that we can perform. One of the tasks that we really were excited about was this notion of disease prediction. So for someone who's getting an imaging study today that is healthy for a given disease, what is the likelihood that they'll develop that disease in the future? We tried to do this for cardiometabolic disorders. We tried to do this with musculoskeletal disorders, things like hypertension, atherosclerotic cardiovascular disease, osteoporosis, etc. And we chose these because we know that there's imaging biomarkers correlated to the disease that are visible in the scan. We just need to be able to extract it and build risk models. Besides that, we can generate radiology reports using the similar approach that I described previously. And we can also solve tasks like semantic segmentation. So really, We wanted Merlin to be a true foundation model because it's been trained in a large-scale self-supervised manner, and it has capabilities to perform a variety of different downstream tasks. So I'll share some results from one of the tasks that I find particularly exciting, which is this notion of zero-shot classification. What this basically means is we can embed an image, and then we're simply prompting that image with natural language to see if there's any interesting findings that are present in there. So we worked with our body radiologists to come up with a list of 30 of the most common findings that they would see in abdominal CT scans. And we're simply visually prompting these particular models with natural language. And here we're seeing F1 scores for the performance of this model across a variety of different diseases. And we can see this in our internal test set, as well as data sets across our different sites. So again, there is no supervised learning that's happening here. This is just the innate knowledge that the model has learned because of the clip training. And we can see that across all the disorders that we're seeing here, roughly the F1 scores in question are anywhere from 0.6 to 0.8. And given that F1 actually respects the underlying prevalence of the disease, many of these are not very common. So if we just use something like AURC, we can just simply predict negatives and we'll have a perfect AURC. So I think an F1 score is more indicative of the underlying value that a model may have. And we're just excited to see that without any supervision, the baseline performance across findings and across tasks is actually across sites is quite high. So this was a really good first step. And yeah, just a reminder that we're seeing F1 scores here. And we also wanted to compare this model to other models that are potentially available in the literature. So as a first pass, we compared this to the Google CT Foundation model, which was released last year, which was claimed to be trained with roughly 25 times more data. And we evaluated the Google CT Foundation model for trying to predict the findings in a radiology report, as well as trying to predict the ICD codes. And we saw that even despite training on 25x more data, we're either on par in terms of performance or significantly better. And we're updating our archive preprint soon too. We're able to run comparisons with a model from Microsoft, their MedImage Insight, and we see similar scaling curves. And we have ablations performed across, at least 15 different model architectures that really shows that this Merlin pre-training strategy works quite robustly. And this for us was very useful to learn because we really wanted to validate our model across data from multiple different sites. There's a lot of data here around how different sites had different data, but let me walk you through what I think is the most important. So first of all, compared to Stanford, whenever we evaluated our data from external sites, the patients were much older at the other sites, which meant that the disease prevalences and the disease burden would be quite different. When we compare Stanford data to site number one, we saw that the imaging protocols, so how the images would be acquired in the first place, were quite different too. This would change what sort of image representations are learned. When we compared to site two, the distribution of scanners was completely different too. And we know that this is a common failure mode for medical imaging models. If you go from a model trained on GE data to one that's being used on Siemens, models typically have some sort of failure modes. And then with site three, we once again had different protocols and we had different radiologist styles in how they report their radiology reports in the first place too. So it was just exciting for us that despite all these differences across sites, our model performed quite well. And beyond looking at generalizability across sites, we're also interested to look at generalizability across anatomical regions, like I described earlier. So we just took our model, which was once again trained on abdominal CT scans, and then we froze the model, or froze the encoder, and we just generated embeddings that we added a linear probe on top of to predict the output of 24 different findings that would be seen on chest CT scans. So we're able to use roughly 50,000 scans from an external site, and then 6 of those we saved for evaluation. And turns out that Merlin has the best performance across all the models that we evaluated, despite the fact that all the models that we evaluated were trained explicitly on chest CT scans. Merlin was trained on abdominal CT scans too. So the fact that Merlin maintained performance across a completely different anatomy was perhaps surprising to us at first, but this just showed that this could be used as a good embedding model that could just extract general purpose representations from a variety of different medical images. So this was some exciting new work that we've been up to, trying to train some of these new vision language models for 3D. But perhaps my favorite part about this model training was we're able to do all this training on one GPU in under a week. We really forced ourselves to be resource constrained, and now we're just excited to be able to scale this up to understand what are the benefits of data scaling, what are the benefits of scaling on model size, now that we have a good understanding of baseline performance. So maybe for the last few minutes or so for this talk, I just wanted to transition a little bit from using some of these multimodal models and going from diagnostic tasks towards more discovery-based tasks too. And this is really inspired by the fact that a data set like Merlin has a lot of different clinical data associated with it. We have obviously the images, but we have clinical notes, we have labs, we have ICD codes. So instead of just solving for known diagnostic and prognostic tasks, can we actually learn something about the underlying disease etiology? Can we use these multimodal models as a lens to better understand physiology too? So this was some of our latest work that is trying to use multimodal foundation models as a new discovery tool. And we're starting off looking at our imaging studies with Merlin, as well as trying to understand all the different ICD codes that are associated with those images. A lot of this work is inspired by this notion of sparse autoencoders that were popularized by Anthropic a couple of years ago. And the high level premise here is that we can basically take these embeddings that come from foundation models that are polysemantic. And what that means is a single, say, 1,000-dimensional embedding contains information about a lot of different concepts. Can we go from this polysemantic features to a different set of features where each embedding only has information about one biologically relevant concept? So that's really going from polysemantic to monosemantic features. And to give some more actionable insights into what this looks like, there's a really nice example from Anthropic a few years ago, where let's say you prompt the model with a question like, "What is your physical form?" And Claude will respond that I don't have a physical form, I'm a language model. But then when you isolate some of these monosemantic features, you can find a feature that is most sensitive to the Golden Gate Bridge, a singular concept. And then once you have this feature, you can increase its weighting in the model. So here they increase the weighting of the Golden Gate feature to 10x. And that would mean that whenever you ask any question, the model will always find a way to incorporate the Golden Gate Bridge in its response. So then, what is your physical form? Well, it turns out Claude is actually the Golden Gate Bridge. So this was just a fun experiment to show that these sparse autoencoders allow you to look for particular features of interest and then be able to perturb those in meaningful ways downstream. So we took that same premise and we use these sparse autoencoders to try to predict future prognostic tasks that a model could potentially be used for. So here, we wanted to see what are the likelihoods of patients developing future findings. And these are the findings that we looked at. So we looked at cancer, we looked at other cardiometabolic disorders. And here, we really set everything up as a FIWA study. Our inputs were a set of different sparse features that we're able to learn from Merlin and the ICD codes. And the outputs were all these particular target diseases that we wanted to predict. And turns out that using these sparse autoencoders with a few different approaches, we're actually able to get a relatively good discrimination between patients who will progress to these diseases or patients who won't progress. So this is just some very early work from the group that are trying to take these multimodal foundation models that exist already and then apply them more in a discovery setting rather than a diagnostic setting. And because we have this nice FIWA study with a whole host of inputs, we can create really nice websites around it too, where we can explore the dense nature of this data. We can look at how we have different image concepts that are associated with them. We can see what those image concepts relate to in terms of risks to make this very user-friendly, because this is very high dimensional data. So the more we can structure and visualize it, hopefully the more we can actually learn alongside our AI models and use the AI models to come up with new medical hypotheses for us. So overall, throughout this talk, hopefully I've shown you that language is actually a really new, useful frontier for us that could be useful across a lot of diverse use cases, be it for language tasks or multimodal tasks, and that a lot of the new tools that we're developing that are fundamentally shaped by the latest advances in AI technologies can just reshape what types of questions we can ask about the underlying physiology of a patient, about their health, and how we can actually intervene meaningfully going forward. But for every new technology that we develop, I think there's a real need to rigorously evaluate these tools so that we really know what is useful and what is not useful and what is actually safe to deploy in the clinic. Pretty much everything that we do in our lab, we want to open source. So I briefly described our checks agent model. It's open source. Our Merlin model is open source too. In case people want some primers, we're able to write up some nice best practices for using language models that could be used even outside of radiology, and just wanted to come up with some definitions for how foundation models are being used in radiology. And last but certainly not the least, all the Merlin work that I talked about, which is our 3D foundation model, is completely publicly available, including the data set. As far as I know, this is the largest data set of its kind, which has the CT scans and the corresponding radiology reports and disease labels that are associated with those patients too. So hopefully this can inspire future work and people building even better models. But Merlin is also available as a base model. I think last time I checked, it's been downloaded over 100,000 times. People have been using it for a lot of use cases. So if you're interested, we'd definitely encourage you to go explore. And with that, I just really want to thank all our funding sources and all the people in the lab that actually make all this work possible. I just have the nice luxury of being able to present their work in front of audiences like yours. So thank you again for your time. Super excited and happy to answer any questions that you may have too. Thank you.
Great. Thank you so much for the great talk. Any questions from the group? There was one in the chat, which I think was just referring to the very first part of the talk. I guess again, talking about errors in the summarization, I think it was like any specific, I get kind of similar to what we talked about before, like typical errors that the machine made that maybe the human does not make.
Yeah, so usually there's this large risk of hallucinations that the model is just adding a lot of detail that is not in the input. We actually noticed that hallucinations were not very relevant or very prevalent, sorry, in this particular setting. There's usually a ambiguity in clinical context. So I think there's this larger notion of confabulation where a model might not have all the clinical context that is required to come up with a clinical diagnosis. So it's hard to call it a hallucination because there is some potentially causal pathway over there, but we're able to actually categorize all the errors that were made. It's all in the manuscript too, but there was nothing that really stood out. It was, which would have been nice because then we can fix those.
Yeah.
But there were just random, it seemed seemingly random errors that would show up across categories.
Okay. Other questions from the group?
Maybe I'll stop sharing. Yeah.
Yeah, go ahead. Freeshank, you can go ahead.
Hi, I'm a freshman at MIT. I found the talk very interesting. I was wondering, is the data you work with like longitudinal in nature? And if so, do you like what you do if there are like gaps in the data, as in like maybe because from what I understood, like are the chest X-rays and the clinical narratives being paired like together over time, or how does it work?
Yeah, that's a really good question. This is a clinical data set, so it is a hodgepodge of everything that you can imagine. Both for the checks agent data set and the Merlin data set, this is basically convenience sampling. We sample all the images for patients as they come to Stanford, Some patients might come just to the ED, maybe because they have stomach pain and they might be suspected to having appendicitis. So they might not even have Stanford insurance, which means that they might not even have their EHR linked at Stanford, but will just have access to the image and the report. That could be one flavor of data sets. Another flavor could be maybe a patient has cancer and they're getting multiple serial scans. That could be diagnostic. Then you're trying to evaluate whether or not your therapy is working. And they might have multiple scans over a large duration where you know everything about the patient. It's a mix, which is good and bad. There is no such thing as a clean clinical data set. So we try to incorporate all the priors that we can. But I really do think that the next frontier for a lot of the imaging work, at least, is not trying to isolate scans in a static moment in time, but really understand how is the patient progressing over time. If they're healthy today, what is the chance that they'll be healthy tomorrow too? If they have a finding tomorrow in a scan, maybe it's not really relevant if they also had it a day before. That's very common in the chest x-ray setting. If someone is in the ICU, they might have a collapsed lung, but the doctors know that already because they had it yesterday. They're just trying to understand whether it's getting better or not. So maybe I digress a little bit, but I think given that this is a clinical data set of true hospital archives data, it's a mixed bag.
Got it. And I had one follow-up question. Um, the data, the data itself, like the EHRs, those could contain like the clinical narrative side of things. Those that could still contain, um, I guess, implicitly contain data from like other tests that the patient might have, right? Other than like necessarily like just having the test result itself, as in like the doctor might mention it or something. Is that possible?
Yeah, absolutely. So, let's say if someone is admitted inpatient, they will have a lot of labs that are ordered by the hospitalists. So you'll have those labs as an independent data point, but then their progress note will probably have some sort of higher order reasoning around what do those labs mean. So I don't think there is any data point that is truly independent. But across modalities, there's a lot of links between this. And I think that's why I'm particularly excited about building tools that can combine information across different modalities because there's a lot of shared content across those.
All right, thank you so much.
Yeah, no worries.
Great, thanks. I think we have time for one more question if someone else has one. 3, 2, 1. Okay, great. Thank you very much for the lovely talk. Just to announce the one that we have next month, we are always the first Wednesday of the month. So our next seminar will be on Wednesday, December 3rd at 2 p.m. It's actually another speaker from Stanford. So we have Dr. Nigam Shah, who's a professor of medicine at Stanford and also the chief data scientist for Stanford Healthcare. So we hope you all can join us next month. And thank you again.
Yeah, thanks so much for having me. Really appreciate it.
Great.
Bye. Thank you.
Bye, everybody.